So folks, welcome to this video that is going to discuss basis and dimension to vector spaces. If you haven't already, please pause this video and go watch the introduction by Grant Sanderson of 3 Blue 1 Brown. He discusses the ideas of span and basis and a little bit of dimension, and I think it's very helpful to start with that visual understanding. So if you haven't paused this video, go watch that one and take some notes to yourself. If you've already done so though, let's go ahead and jump into our delivery of the topic. And I want to remind you of the definition of a linear combination. So we're going to say that a vector W is a linear combination of a collection of vectors if we can write W as this way. So if W is equal to C1 V1 plus, say, I don't know, C2 V2, we might have a whole collection of them, all the way up to maybe some CK VK, then we say that W is a linear combination of V1 through VK. So put another way, if I can write W as a sum of a collection of vectors or scalar multiples being multiplied to a vector, if I sum it up, then we say W is that linear combination. So now I'm ready to define the word span. So let's just say that. So a span of a set of vectors V1, V2 up to VK, the span of these vectors, which we'll denote as the span of V1, V2 up to VK. So the span of a set of vectors is just all linear combinations of those vectors. So here W is a linear combination of the vectors V1 through VK, so we'd say that W lies inside of the span of that. Okay. One thing we'll discuss later is that the span of a set of vectors is indeed a subspace of V, meaning if I take two vectors that are already in the span of V and I add them together, I get a third vector, and that third vector would be in the span. Or if I take a vector and I scalar multiply it by some scalar, that new vector would also be in the span. That's what we mean by vector subspace there. Okay. So let's go ahead and look at these two vectors. We've got U and we've got V, and let's give a typical element that would be in the span of UV. So the typical element that would be in the span of UV would look like maybe some W, let's say W1, or say W here, which is C1 U plus C2 V. Another way to write that would be C1 times the vector U, 3, 2, 0, plus C2 times the vector V, 0, 2, 2. So for example, if we picked C1 is equal to -1 and C2 is equal to 2, let's see what we get. If C1 equals -1 and C2 is equal to 2, what would we have here? We'd have this new vector, maybe we call it W1, and that would be equal to -1 times 3, 2, 0, plus 2 times 0, 2, 2, and we could actually find that vector that's in the span of U and V. Because why? We know that W is a linear combination of U and V, and so that resulting vector by definition is in the span. That resulting vector would be the vector, let's see here, -3, 2, 4 would be that resulting vector. We'll remember that for the next page. Okay. So what do we mean by, let's just say that one more time. What do we mean by the span of a set of vectors? A span of a set of vectors is just all linear combinations of those vectors. In terms of geometry, if I give you a collection of vectors, maybe I give you two vectors here, in terms of geometry, the way you could think about that is the span is all of the other vectors that you could reach by linear combinations of these two vectors. So in the case of two vectors in R3, the span of two vectors of R3 is the plane of vectors that you can reach simply by either scaling vector U or scaling vector V and then summing those together to get a new vector in the plane. That's what we mean by the span. Okay, let's do a little bit more work with that. Let's take this span of UV. We'll use the same U as before. So I think we had that U was equal to, from the previous page, we had U was equal to 3, 2, 0. And V from the previous page was 0, 2, 2. And so we before talked about the span of UV. Let's take this new vector, W1, and let's create the span of UV W1 and see what we get. And let's go ahead and let the cat out of the bag here. We actually saw this vector just on the previous page where we said that W1 was just equal to minus U plus 2V. That's what we saw on the previous page here where we took, when we let C1 be -1 and C2 be 2, we found that W1 is already a linear combination of these two vectors. Okay, so put that on the back burner. Let's just pick a vector A in the span of this new set, the span of U, V, and W1. So I'm just picking any old vector that's a linear combination of these three vectors, and let's see what we can see. Well, by definition, that would mean that A is equal to C1 U plus C2 V plus C3 W1. But what did we say about W1? We said that W1 itself is already a linear combination of vectors U and V. So I could write W1 as minus U plus 2V. And if I do some distributing and collecting of terms, I would have C1 minus C3U plus C2 plus 2C3V. And notice that this is just an element. Let's write it right here. That's an element that's already in the span of UV. So what I'm trying to say here is that we took all the vectors we could reach as linear combinations of U and V, and we threw a new one in. We threw in a new vector. And it turns out in this case, we're not able to reach any new vectors through linear combinations that we couldn't before. And why was that? The reason why that was is because W1 here was already a linear combination. It was already in the span of UV, so throwing that vector in doesn't allow me to reach any others. Put it another way, W1 is not linearly independent. I'm going back to that word here. W1 is not linearly independent from the vectors U and V, and so adding it into the span set did not allow me to reach any new vectors. So we just said that the span is all linear combinations of U and V, and since W1 was already a linear combination of U and V, adding W1 to the list of vectors doesn't change its span. That summarizes what we saw on this previous page here. Okay, well now let's go look at this other vector, W2. Let's first ask the question, notice the key over here was we already knew W1 was in the span of U and V, and so we didn't get a larger set. Let's see whether W2 is in the span of U and V already. So let's go find out. Well, for W2 to be in the span of U and V, W2 would have to equal, so are there C1 and C2 so that we would get C1U plus C2V is equal to W2. That is, can I find a linear combination of vectors U and V so that W2 is equal to that linear combination? If I can, then what? W2 is in the span. But if I can't, and we'll see what happens, if I can't find a C1 and C2 to make that true, then we would conclude that W2 is not in the span of U and V. It's not one that we can reach out and touch from linear combinations of U and V. So let's find out. Well, let's see here. We could set up an equation here where we've got W2 is 1, 1, 0, that vector. And we're asking, can we find C1 times vector U, which vector U was 3, 2, 0, plus C2 times vector V, and vector V was 0, 2, 2. And let's see if we can solve this system of equations. Notice that the first row would correspond to 1 equaling C1 times 3 plus C2 times 0. And we can build a system of equations. Here would be that system of equations. We would have 1, 3, 1, 2, 0, 0 times C1, C2. And we're asking, can we, I made a mistake there, folks. That should be 3, 2, 0, 0, 2, 2. Taking these two vectors. Does that equal the third vector, W2? So 1, 1, 0. Okay. Well, we can set up this system as an augmented matrix and row reduce it. So we'd have, make that a little bit bigger, 3, 2, 0, 0, 2, 2, and we'll adjoin it with 1, 1, 0, and we will perform the row reduction. So I'm going to let you do this. So you check this. But when you get done performing the row reduction, what we end up with is 1, 0, 1/3, 0, 1, 1/6, 0, 0, minus 1/3. And what do we know about this system of equations? We know that there's no solution to the system. That's what we literally mean when we perform the Gauss-Jordan elimination method on this system of equations. We found there's no solution, but what does that correspond to our original question? We were asking, can I find a C1 and C2 so that I can express this vector as a linear combination of the other two? And no, I can't. There's no solution to that equation. So what do we conclude? W2 is not in the span of U and V. So that, if you go back to that analogy, these are vectors in 3 space. If you go back to that plane analogy that we had before, you have these two vectors, U and V. And if you look at the plane that's spanned by those two vectors, the third vector, W2, is not in that plane. It extends out of, it's not in that plane, and so it's not a linear combination of those two vectors. Note that another thing we could say is that in showing that W2 wasn't in the span of U and V, we've shown that the collection of vectors U, V, and W2 are linearly independent because U and V are not multiples of each other, and then we've just shown that W2 is not a linear combination of the first two. So these 3 vectors are linearly independent. So let's do one more question with this set. Let's go identify what is actually in the span of this new set UVW. So let's take all the vectors we can reach with that. Let's just say that we take C1 times U plus C2 times V plus C3 times W2, and let's just say that the result of that is some vector A, B, and C. Let's go see what we would notice if we try to figure out what A, B, and C have to be. So we go ahead and set up the system of equations. Now folks, what I'm going to do here is I'm not going to go ahead and, I started out writing it this way, I'm not going to go ahead and take the time to write this out in terms of a vector equation and then set up the matrix this way. Instead, I'm just going to jump straight to the augmented matrix, where we would take vector U, which is 3, 2, 0, vector V, which is 0, 2, 2, and vector W2, which is the vector 1, 1, 0, and we're going to join this with A, B, and C. So I could now perform the row reduction algorithm on this, and I'll go ahead and put this out for you. I'm not going to say it as I write it, I'm just going to perform it, and then I'll speed up the video. But go ahead and perform the row reduction algorithm on this yourself and see what you get. So folks, I went ahead and performed the row reduction algorithm for some arbitrary vector here, and notice that regardless of what A, B, and C were, when I perform the row reduction, I do end up with an augmented matrix with how many pivots? We've got 1, 2, 3 pivots, so this will always have a solution. This will always have a solution. Regardless of A, B, and C. So, since A, B, C was just an arbitrary vector, the span of U, V, and W2 is actually all of is all of R3. That means any vector in R3, any vector that has these 3 coordinates here, can be obtained as a linear combination of these 3. That was not the case when we were just looking at U and V. When I just took U and V, I wasn't able to reach all of the vectors in 3 space. However, if I take U, V, and W2 and look at the span of this set, I am able to reach, because this always will have a solution, I am able to reach all of the vectors in R3. So the span of this set is just R3. Okay, folks, that gets us through the idea of span, and now we're going to add that idea to the topic of basis, and we'll do that in the next video. Thank you very much.